are a couple of rules that will help you to know what kind of curve to use and to help make your decision. And realize, number one, there is no one correct answer that solves all of them. Look at this one right here. See how this curves like that? Well, it could be that you could map a square root function to do this. A log function could do it. It might be an x to the 5th function. There are a lot of different functions which would go through this data. And as long as all those choices are going through the data, you'll get good predictability with either one. There isn't just one answer, but all of the correct answers will be close, and they will get you close to the same predictability. Now, knowing that there are more than one correct answer isn't the same as saying anything can be a correct answer. There are models that are wrong. For example, a straight line. It doesn't fit a line that curves. So even though there might be more than one correct answer, that doesn't mean you can do anything you want. You have to find one of the correct answers in order to be able to give the client what they want. And when you're looking between all of these good models, don't use R-squared to choose which model it is that you want to use. There are lots of ways that R-squared can be fooled, and we're going to talk about that more in future chapters. But R-squared being high does not mean you have a good model or a correct model. So what you would like to use, ideally, is the true theoretical form of whatever it is you're studying. If you go to the experts and you say, it seems to be curving like this, and they'd say, oh yeah, it's supposed to have a square root function. Okay, that tells you the model to use. Or if they said it should be log, great. Now in this class, you're purposely not going to have an expert that you can talk to. And so you won't know, is it square root or is it log? And honestly, that's kind of realistic. A lot of times the expert says, we don't really know. We're still trying to explore how this relationship works. So in real life, we'd love to have theoretical explanations. You're not going to get a lot of that in this class. So the first thing you want to look at is, how do those residual plots look? Those residual plots will tell you, have you accounted for all the patterns in the data that you could find? If the residual plots do not look good and you have a great R-squared, you do not have a good model. You want to continue to upgrade it until you get residuals that are as good as they can be. And by good residuals, I mean they should just be random scattered. You shouldn't be seeing any patterns left in there. You might find good residuals with two different models, maybe a square root and a log, and you have to choose between them. Well, make sure that everything in your model is significant. If there's anything with a large p-value, that large p-value suggests it's not actually helpful to the model. There's no reason to keep it in. You might as well trim it down. And when I grade the final project, I look, do your residuals look good? Are all your p-values small? There are exceptions to this rule where you can have large p-values. And we saw that in the last video sequence where we had different slopes, but the y-intercepts were not significantly different. And you could choose to leave those different y-intercepts in, but you need to be able to explain, I left the different y-intercepts in because the slopes were different, telling me that these categories do matter, and so I left those in. That's what I'm grading. If you had large p-values, can you explain why you left those large p-values in there? And one example of that we're going to see in this section is what happens if x squared is significant, but the x not squared term is not significant. Well, you can choose, and people argue about it, and there's reasons why you might choose one way or the other. For example, some statisticians would argue you should leave it in. And that way, when we talk about quadratics, you're allowing for any type of quadratic that's needed. It's more versatile. The fact that the p-value was large doesn't mean that you want to restrict what types of quadratics can be used. They would also argue that if x squared is needed in the model, then x obviously has value, being squared. So let's just let x stay in there. They're saying theoretically we think x does need to be in the model, even though the data didn't happen to show it significant. But other people would argue, throw it out, because that's what we do. If your p-value is bigger than alpha, then we throw out that variable. And that does make your equation a little bit shorter. Does that make it a little easier and simpler to explain? Well, if it does, they would argue throw it out. These are often more applied practical statisticians. These are the more theoretical, mathematical type statisticians, and they'll argue about it. Which one's the right one? Well, you get to pick. Now, once you have chosen your model, you've got good residuals and good p-values, if you still have two different models which are equally good, you might try whichever one you can explain. If you have a model that is x squared and another model that is the sine of x over the log of 1 plus x, I don't know really how to explain the sine of 1 over log plus whatever. Mathematically, sure, I can do that, but can I explain it to the client? So if you have two equal models, look at which one is easier to talk about, and you can go with that one. Now, the last rule I'm going to put on here involves the term fishing. Fishing is when you start trying stuff. I'm going to try an x cubed, next to the fourth, next to the fifth. I'm going to try log of x to the fifth. I'm going to try the square root of x to the fifth. And you start throwing in all these different things. That's called fishing. There's a danger to this. You can eventually start to find patterns where none exist. If you took a screenshot of pure static and stared at it long enough, eventually you'd start to see faces in there because that's how humans react, and it's really creepy. So you don't want to do this in real life and in higher level classes. You don't want to try 500 different models and see which one you like. I'm not sure that's really a good idea in this class, but some students aren't sure, they feel insecure, and so they want to try this model and that model and the other model. Okay, in this class, because you're still learning how to do model selection, we're going to say that you're allowed to do fishing. There's a phrase in statistics. We say, if you torture the data long enough, it'll scream anything you want it to. What I mean is, if you try x squared and it wasn't significant, and you try x cubed and it wasn't significant, x to the fourth, x to the fifth, x to the sixth, eventually you'll find some x to the something that is significant, just by random luck. Do you really believe, theoretically, that the model needed x to the 47th power? Well, no, but by fishing, you lucked into something that worked. Okay, I understand that you might do that, and in a higher level class they would say, come on, let's not throw in junk just because you lucked into finding something. We want to avoid fishing and try doing what we actually think the model really needs. You're learning, so we'll allow it. In the next video, let's actually show you how to do some of this curve regression in R.